안녕하세요. My name is Steve Kohalmi. I work in the Juniper CTO architecture office. I work on a couple of technical topics, focus on those topics, such as mobile network security and IoT. And in this talk, I'd like to look at what IoT security networks are like, why they are kind of like what we do today, every day, but why they actually also different, how they're evolving. IoT security has real-world implications. It's different from what I normally do. I normally connect to the office, connect to my bank, I stream something from Netflix. Security of those are important, but not important, life-threateningly important. It is when your pacemaker is connected to the network, or like on the picture here, that a Jeep ends up in the ditch. Those are actually much more important. The value of that data that's being transferred between those IoT devices and the network is more important. And the importance comes from the trust. You want to know who you're talking with on both ends, and you want to trust the data that's coming. Make sure that the data, where it's coming from, who's sending it, and nobody modified it on the way there. Without trust, data is useless. It's useless because there is no value to it. At best, it's useless. At worst, it's actually dangerous. The other aspect is privacy. It's data that somebody can read in the middle, somebody can use it, somebody can copy in the middle, is actually, it loses its value. It loses its intellectual property. It actually gives away personal, private information. So encrypting the data is essential. But IoT networks are not just different from the application point of view. They're different from what the networks look like, what you see in the networks, different how IoT networks and their applications want to process data, and also different from the perspective that there are new IoT devices are evolving continuously. And I will talk about here one specific case, which is the constrained devices. Firstly, the IoT devices talk to applications, talk to services, somewhere in the cloud or somewhere processed. Typically, the network in between doesn't know what's happening with those IoT devices. The IoT devices hide behind or obscured by NAT devices, routers. They're obscured by end-to-end encryption or by large-scale tunneling. So the networks in the middle are blind to the data. And that's a really big problem because a network service provider would really like to understand what sort of traffic is going through, who's talking on the network, what kind of behavior they should be doing and shouldn't be doing. They want to be able to defend their network. They want to be able to plan for what the network should look like in the future. And of course, they want to be able to bill for that, for the traffic, meaning want to charge for their customers. So it is a complex problem, and it becomes even more complicated with scale. Scale of IoT networks is significantly larger and is ever growing compared to the human traffic. So normal practices of how we manage networks today are just not going to work any longer. Rules, signatures, rules of thumb just won't work any longer. Fortunately, IoT devices, IoT device management, IoT networks is a problem that actually is really applicable, and it's a really good problem for artificial intelligence and analytics. The fortunately comes from that IoT devices are not like humans. IoT device communication is not like human-to-server communication. When I communicate, I have my handheld, my smartphone. I have 15 different apps running on it. I'm in front of my computer. I have a web browser open. I have email running, and all of those things are doing different things, generating very different traffic. An IoT device is simple. They do one thing. It does one. A temperature reader, a temperature monitor does one thing. It monitors the temperature and periodically sends sends its reading up to the server. A video camera, a security camera, all it does is it transfers and it records and transfers video feed up to its server. So they all do the same thing. And you can create this large cluster of equipment that actually does, they all do the same thing. The whole cluster does the same thing. And they keep doing the same thing until something happens. That something could be a new software download upon which all the devices change their behavior, but they change their behavior all of them together. They do it at the same time, and they follow the new behavior is predictable from that point on. But it's really nice because if some of the devices actually get infected, then you see that suddenly the group split and they start to and then you can peel off the devices that are actually malbehaving, right? They don't do the right thing. So this is a great problem. These sort of networks are a great problem for analytics, for machine learning and artificial intelligence. Let me run through one of our examples. On this picture, I have a bunch of refrigerators, and they are connected to different networks. Some of them are connected to a mobile network, a mobile service provider's network. Some are coming through business networks or some private landline connection, fixed connection. So firstly, the refrigerators are infected with the malware, and they initiate a DDoS attack on the data center up on the left corner. We detect that a DDoS attack is happening at that point, just by the volume of traffic, the type of traffic, but we don't know what to do with it, right? We can't tell the difference between the attacking traffic and the good traffic. So, but fortunately, we also detect that something is going wrong at the edges of the network. We have firewalls everywhere at the edges of the network. They report up into the cloud, right? And in the cloud, we apply all kinds of techniques, from GSA to ATP to other analytics techniques, and figure out that there is a DOS attack that's happening, and after then have some idea what to do about the DOS attacks, how to prevent it. Then that from the cloud, we report this to the policy enforcer, and the policy enforcer looks at its policies, and after then also understands the network topology, and it figures out where to enforce where to stop the DOS attacks, where to do that, and in this case, do it at the edges of the network, not at the data center, but all around the edges of the network. So stop the traffic, block the devices, quarantine them, and etc. And that's happening right there. Another aspect of IoT networks is that they're not necessarily end-to-end. I kept talking about end-to-end networks, but that client-to-server model works well for humans. But they don't necessarily work so well for IoT networks. IoT devices and IoT processes would like to see something different. They want to see distributed processing, whether the distributed processing is on the premise or at the edge of the service provider network, but they still want to see that those applications distributed. There is a really famous blog around that I don't remember who wrote, that talks about the death of cloud-based computing. Everything they're getting distributed, moving to the edge. So why distribute? Firstly, we want to distribute because of latency. Low latency is essential, for example, for augmented reality. If you look at applications like Pokemon Go, or applications like a repair technician using augmented reality glasses, they want to be able to look at the real life and overlay virtual pictures, virtual information right on the top of that. To do that, to actually follow somebody around and able to follow the person's movement, head movements, location, etc., and realistically put the overlay on it, you need very, very low latency between the processing the information and the actual person. Imagine a repair technician who goes to who goes to one of those Caterpillar generators that's in the picture and needs to repair it. Puts on the glasses, and after that starts walking around, figuring out which piece is which component is which, where are the, and after then in the background, the analytics is getting done about trying to figure out the root cause of the problem. And all that information gets conveyed in real time over the glasses. To do that, you need sub-millisecond latency. Sub-millisecond latency is not possible if all the information goes to the cloud and comes back. That's where edge computing latency really matters. The other place it matters is that all the devices all these manufacturing and other equipment generates enormous amount of data. There is the famous number is that a GE jet engine can generate 1 terabyte of data per hour. But closer to the ground, right? The Tesla car can generate 10 gigabytes of data per day, and all that gets uploaded into the cloud. A generator like the one I previously described has hundreds of sensors on it. All of them keep sending their reading up into the cloud. It's not that, firstly, a lot of that data is nothing else, just junk. There is no value to actually transfer it to the cloud. The other aspect of it is that it's expensive. Every bit that gets transferred through the network and the backhaul network is built for, charged for. So it's very expensive. It makes a lot of sense to actually pre-process the data at the edge of the network and really only send data up into the cloud as it's necessary, as it's required. But once we're moving applications to the edge of the network, we actually no longer just have a single edge router, a single IoT gateway. What we have is we created a data center at the edge of the network. And when we have a data center, we need data center-like security. So you can no longer just secure the local area network, secure the backhaul network, and that's all it takes, a simple little firewall. What you need is really, in addition to those network security, you need to secure all the applications, and actually including security in the service chain. And also have to look at multi-tenancy, that this is not a single service chain, but multiple service chain. One example of this is a project we're doing in Germany. This is a V2X, vehicle to anything, lab that the German government initiated. It's a very large test track with all kinds of intersections and then buildings and etc. in the middle, trying to simulate the environment, what it would take for automated cars to travel around the city. And the point is that you have a lot of small base stations, right? Small cells, and they are connected to the cars, they connected to the roadside infrastructure, and then continuously talking to all these devices. It is impractical, impossible, and unwanted that all of these devices talk to one another via the cloud. What happens is they actually multiple hubs get set up around this area, and they do computing there. So all the devices actually talking through these hubs, but then these hubs require security, they require the IPsec termination, and then they also require additional services such as legal intercept, and they be able to transfer state between one another. It's a really interesting project, it's a complex project, but real world is going to look like this, and you need to secure that real world. The coming of IoT not only changes the network, but changes the processing in the network. It also requires different devices. Generating IoT devices generate tremendous amount of data, and that data is being consumed by big data analytics. And the combination of IoT and big data analytics is a tremendously powerful development, one that actually has significant economic value. But as the big data revolution is churning up. And analytics and machine learning, artificial intelligence, they need more and more data. They're trying to get more data. So what the world is doing is tagging almost everything with sensors. We have sensors on containers, sensors on packages, clothing, environmental sensors in every room and anywhere in the world. But that model only works if the sensors are really cheap, they're really small, they operate on batteries, so they have very low power consumption. So these are constrained devices. And that the constraint problem also not just it also carries on to security. It's not that the security is optional. It's not that security is constrained from the strength of security perspective. It's constrained from perspective how much processing it can take. So security is just as important, but we have to change the way we do security. We can no longer secure our traffic with TLS and an IPsec using certificates. They're just too complicated, too much overhead. The 3GPP standards, which is the 3GPP standard is the mobile network standards protocol body, realize that they have to make changes. They have to adopt the cellular networks to IoT. And they attack this from multiple aspects. From the radio perspective, from the RAN perspective, they developed LTE-M and narrowband IoT, and then those actually, they optimize the network for massive number of devices, for deep penetration underground locations, and also optimize when they turn on and off. The control plane also cuts away the number, limits the number of messaging that's happening, and also lets the devices to go to sleep for extended periods of time. In the security group, we started work to change the way we do security for IoT devices, to also optimize that, getting rid of certificates and IPsec, and after then creating a new protocol. This new protocol is called BEST. For short, it stands for Battery Efficient Security for Very Low Throughput IoT Devices. And the standard is coming out middle of 2018. So let's see how BEST works. Firstly, on the right side, we have the IoT devices, and on the very left side, there are the services they're trying to connect. In between, there is the mobile service provider network. I have a new device encircled with red that is what we call the HPLM, the Home PLMN Security Endpoint, the HSE. And this is a middle box where we want to be able to manage the security. So let's see how this works. Firstly, an IoT device has to connect to the mobile service provider's network. This is standard. This is how every phone works. The device has a SIM card in it with a secret. It connects to the mobile service provider network, and the HSS, the home subscriber server, has the same secret. The two of them share this secret. This is the pre-shared key. And they exchange some messages and authenticate one another, verify that they both have the same key, and after then at the same time they generate some additional keys for the session that they use to encrypt their communication. But now the IoT device also wants a similar kind of encryption go to the HSE in the middle of the network. So it sends a packet to the HSE and says, I want to bring up EMSDP, which is the new control protocol with you, but the HSE doesn't have the key. So it goes up and the wrong direction. The HSE doesn't have the key, so it has to go to HSS. HSS, get the key, and after then they both have the same secret, they both have the same keys, so they establish a tunnel, encrypted tunnel between the IoT device and the HSE. So this is an end-to-middle encryption. The nice thing about it is that it works when the device is roaming. It actually can do integrity protection only, no encryption, and it allows the service provider on that middle box to provide services, IoT-related services to its customer. And those customers don't have to worry about managing the identity of the devices, managing their security. The service provider takes care of all of that. The smart building that's on the picture has thousands and thousands of low power sensors on it. It's only possible, those sensors are only possible because when they deployed, nobody has to worry about where the power is coming from, where they're located, any of that. They're just simple devices all around the building. But the point of that is it creates an incredibly, all those sensors in a building and the local processing creates an incredible, powerful business proposition. It creates an incredibly powerful building. That building knows what the temperature is in each room, what are the environmental characteristics, knows when somebody's coming in, knows when somebody's leaving, knows where every person, in which room they are, where they're going. They also know who they're talking to because they listen. They also know who they are. There's face recognition and there's voice recognition and everything is recorded. So with that sort of power also come challenges and also come problems. So this kind of ubiquitous network really requires ubiquitous security. Lastly, there is a lot of hype around IoT, but IoT is not a hype. It is really creating a whole new paradigm, whole new model for IoT networks, for processing, for devices, and but at the same time, it requires security, and that security needs to be built into the devices, the applications, and into the networks themselves. Thank you. Gamsam Hamnida.